All right, let's pull back the curtain on modern technology, and I mean really look under the hood. There's this silent engine that's driving the entire AI revolution. You know, from your phone's camera to these massive language models everyone's talking about, it's all powered by one fundamental idea, the computational graph. But to really get why these graphs are so important, we have to start with the more basic question. When an AI gets something wrong, how on earth does it figure out how to get it right the next time? I mean, how does a machine actually learn?
Well, the answer isn't some kind of mysterious black box. It's not magic. It's actually something way more elegant and structured. It's a map, a really detailed blueprint of every single calculation that, and this is the key part, lets the machine trace its steps backward to figure out where it went wrong.
Now, to really appreciate why we need this map, you've got to understand the problem we're trying to solve. At its heart, training a modern AI is like trying to solve a math problem that is, for all practical purposes, impossible to do by hand.
Look, we're not talking about one equation here. We're talking about adjusting billions of tiny little knobs, or what we call parameters, all at the same time. And the only goal is to make one number, the error, go down just a little bit. Trying to track how each of those billions of knobs affects the final answer, it's a computational nightmare. You'd be totally and completely lost.
So, what's the solution? Well, instead of trying to wrestle with this one gigantic, messy equation, we map it out. We break the whole thing down into a simple visual structure. And that is our computational graph. Okay, so the first building block of our map is called a node. Just think of a node as one single landmark on our journey. It could be a piece of data, like a variable x, or it could be a simple action, like addition. Each node is just one tiny, super manageable step in a huge process. And what connects these landmarks? Well, those are the edges. An edge is basically the road between the nodes. It shows you the direction of traffic, how the data flows from one operation into the next. It's literally what gives the entire calculation its order and structure. Let's make this real with a quick example. Say we have the equation z equals parentheses x plus y times w. So first, we create input nodes for our variables, x, y, and w. Then an edge connects x and y to an add node. Simple enough. The result from that flows along another edge to a multiply node, which also takes in w, and boom, the final output is our answer, z. See? Simple, clear, and perfectly organized. But here's the thing. The real magic of this map isn't just about getting to the answer. It's about figuring out how to find a better route for the next try. This is where the graph's true power comes in. Because by building this structure, the computer isn't just spitting out a number. It's actually creating a detailed record of every single step and every dependency along the way. It remembers the exact path it took. And that memory, that is the absolute key to learning. This whole setup gives us two critical processes. You've got the forward pass, which is pretty straightforward. You're just following the map to get your answer. But then you have the backward pass, and that is where the learning happens. This is where the machine literally walks backward along the very same path it just took. Right, this backward journey has a famous name, backpropagation. Using some good old-fashioned calculus, the algorithm goes backward from node to node, and it calculates precisely how much each little step contributed to the final mistake. The graph makes this process incredibly efficient. It tells the machine exactly which of those billions of knobs to turn and by how much to get a better result next time. It's what automates the whole learning process.
So how do programmers actually build these things? Well, it turns out there are two main schools of thought here. You can either create a whole detailed blueprint in advance, or you can kind of build the map as you go. And this difference is actually a really big deal. You have frameworks like TensorFlow that were famous for static graphs. Think of this like that pre-planned blueprint. You define the entire calculation up front. This lets the system optimize the whole path before it ever runs, which is super efficient for production models. On the other hand, you have PyTorch, which made dynamic graphs super popular. This is more like building on the fly. The map gets created as the code is running. It's way more flexible and easier to debug, which is why researchers absolutely love it for experimenting with new ideas. So if we take a step back, it's pretty clear that this idea of breaking down a huge problem into a graph isn't just some clever little trick. It's really the foundational engine that powers all of modern AI.
And you know what? Its impact goes way beyond just neural networks. This core idea, representing processes as a graph of nodes and edges, it powers all sorts of things, from complex scientific simulations to the very compilers that translate our code into something a computer understands. It's a fundamental concept in computer science today. The computational graph really caused a huge shift in how we think. It let us move away from these giant, messy, monolithic equations and start thinking in terms of clean, modular operations. It took us from the impossible chore of doing calculus by hand to the almost magical world of automated learning. And by laying out the structures so clearly, it let us see which parts of the calculation could be done at the same time, unlocking the massive power of parallel hardware like GPUs. And this really gets to the heart of it. As one source puts it, these graphs let machines understand the structure of the computation itself. It's not just about getting an answer anymore. It's about understanding how you got there. And that structural understanding is what makes this whole automated learning thing possible in the first place. So, the next time you see some new AI doing something that seems absolutely incredible, just remember that elegant, silent structure working behind the scenes. That organized map is what turns an impossible math problem into a solvable learning task, which of course leaves us with a pretty fascinating question to think about. What else can we teach machines now that we have a map for their thoughts?